Hello and welcome to this section. In this section I will provide an overview about machine learning to you. You will learn how machine learning differs from classical programming approaches and which different types of machine learning are available. This visualization shows the difference between classical programming and machine learning. In classical programming, a human, the programmer, takes data and defines rules by hand and bundles these rules into some algorithms to get some results. Machine learning is completely different. It reverses the order. Data is provided together with answers. We will call these answers target variables to an algorithm, and the algorithm detects the rules and bundles them into some model. It transforms input data into useful outputs. The process is called learning. For this, the data has to be transformed in some useful way. How does the machine learning algorithm do this? Let's take a look at some example. You have some data in a two-dimensional plot, specified by the axes x and y. The dots represent observations and the colors correspond to their classes. There is a red class and a blue class. There is a red class and a green class. Here I rotate and translate it. We have a new coordinate system x prime and y prime. The relative positions between points are not changed. But take a look at the points and their relationship to these new axes. All the red points are characterized by positive x prime values, and all green points are characterized by negative x prime values. Actually, this makes the classification task much easier. Just follow these rules. Assign a new observation to the red class if x prime is larger than 0, and assign it to the green class if x prime is smaller or equal to 0. And now imagine you have a new measurement point. How can you know if this belongs to the green or to the red class? Now this is easy to answer, according to the rule that was discovered. It belongs to the red class. On this map you can see a classification of machine learning models. You have unsupervised, supervised, and reinforcement learning as different learning types. Another dimension focuses on the target variable. It might be categorical or continuous. Different machine learning techniques fit into the different boxes. The most relevant types are regression and classification techniques. Regression is a type of supervised learning where the target variable is continuous. If the target variable is categorical, we have classification models. There is also unsupervised learning, in which we don't know the target variable. We rather want to reveal patterns in the data. Let's get a better understanding based on some example. Assume you have information on students from a school class. There are different students, different learning methods, classes, and the corresponding grade. In supervised learning, the task is to use certain labels or target variables for prediction. Here you can see the grade, which is the target variable and should be predicted. So that would be an example for a regression task. Now what happens if you create a visualization of math and sports grades? There is a cluster of students with good grades in math and bad grades in sports. Another cluster is found for poor math grades and good sports grades. These clusters don't have labels, since this is unsupervised learning. It is an example of clustering, a special technique of unsupervised learning. Here, it is up to the analyst to provide some labels to the patterns discovered in the data. Let's call the first group nerds and the second group athletes. There might also be other students which don't fit into these clusters. Another technique is reinforcement learning. In our example, we have two different learning methods, A and B. Assume you don't have all observations right at the beginning, but you assign a learning method to each student one by one. The task is to find out which learning method should be chosen for subsequent students. There are other techniques like A/B testing, but specific reinforcement learning techniques find a solution much faster and are thus much more efficient. And if you want to predict the performance of students, you start training an algorithm based on existing student records. And now it depends on the fact if you want to predict a categorical variable, a simple pass or fail. In this case, you want to solve a classification problem, or if you want to predict specific percentage scores or grades. In this case, you have a continuous base of the target variable, and you want to solve a regression problem. Here you can see a different comparison of classification and regression tasks. You can see two different independent variables, x1 and x2, on the left side of this graph. The colors are representing the class groups. The classification algorithm tries to find a decision boundary between the groups, indicating here as a black line. At the right side, you see one independent variable x and the target variable y. The blue points represent the relationship between independent and dependent variable. The relationship here is linear, and the algorithm finds model parameters to describe this black line, which represents the points best. Here is an example from our student dataset. The output of the target variable is discrete for classification, and it is a continuous number for regression models. In our example, this might be fail or pass grouping for classification. And classification models search for decision boundaries for defining the group memberships, where regression tries to find a best fitting line. Which evaluation measures can be taken? There is, for example, accuracy for classification tasks, and there is R-square for regression models. But within this course you will learn much more. So that's it for this lecture. Thank you very much and see you in the next one.